Good morning to everyone, both to those physically present today here and to those connected remotely to this event. Thank you for being here. Today, first of all, it is a pleasure for me and for my colleague. It is an honor to be here at the Italian Pavilion during Expo, during the Space Week, to present our event, Earth Observation from Space, from physical principle to advanced application. Today we will talk about the technology for the Earth observation of space to observe our wonderful planet. We will start from the description, the basic physical principle underlying the possibility to monitor, to observe the Earth remotely, and we will continue with the description of some of several advanced applications. Why we decided to talk on this topic at Expo 2020? I will start to the motto, I don't remember, I write it, connecting minds and creating the future through sustainability, mobility, and opportunity. Few things like space motivate people. Space system stimulate people imaginations. Space, its content, its exploration, the possibility to monitor this planet, moving the frontier of knowledge further. The space is capable to do that for the people. In this context, remote sensing has helped us to shape the future by contemplating the sustainability of the environment from the environmental terms, a value, the environment that is being discovered in recent years. Monitor the Earth to understand the planet, to monitor it from the forest to seas, to glacier, to urban environment is very important from the sustainability point of view. So these technologies are very important to stimulate the progress, to move the progress further. Also, the motto of the Italian pavilion, beauty connect people, the beauty of the Earth, the possibility to monitor this wonderful planet is also important to stimulate people and to join the people, the researchers from the university, industries, to work on remote sensing. So I will start now with the presentation, the introduction of this event. This event is organized by my university, University of Naples Parthenope, from University of Pavia, University of Trento, and CNR IREA, that is an institute of the National Council of Research. What is remote sensing? Basic for the people that are not very expert of this technology. Remote sensing is a class of technologies that allows to obtain information of the environment, of object positioned, placed far, remotely from the sensor by sensing the electromagnetic radiation of different kind. We can do a lot of things. We can observe a lot of different environment. We can monitor risks. We can monitor, for instance, structures for safety. We can monitor agricultural fields. Or we can monitor the sea, or, as mentioned before, urban environment. So these five are only few among the several applications fields of remote sensing. Just a few words about the history of remote sensing. The first aerial photo was taken more than 1.5 centuries ago, and was taken by a French guy, Nadar was the nickname of this person, that was the first to take an aerial photo of in France. Unfortunately, we do not have the first photo preserved because it was not stored in some way, while the first that was stored is a photo always taken from an air balloon 2 or 3 years after the French guy, and this guy was James Wallace Black, And he entitled the first photo, Boston, as an eagle, and the wild goose see it. So from a balloon, like a bird, to watch the city of Boston. This is the past. What is the present? There are a lot of possibility to talk about, but I chosen the second generation Cosmos Skymed. Cosmos Skymed is the Italian constellation, is the second generation of the Italian constellation of satellite, and this is one of the satellite of the second generation, and this fantastic photo, this fantastic image, is the image of a detail of Paris, details of Louvre Museum, and you can appreciate the very incredible spatial resolution of this image. So in 1.5 centuries, we make a lot of progress in this field. Very briefly, I want to introduce the different kind of technology that we can use in remote sensing, because in the first part of this event, in the first part, we will talk about the physical principle that underline this technology. So more or less, there are two main possibilities: to use passive sensors or active sensors. Passive sensor, as you see, use a primary light source and register the reflection from the Earth, from the different material in different way. The active sensors use as a sensor, the sensor is used also as a primary source and recover the signal after reflection. So in the first class, we have both mainly optical sensor. In the second class, mainly radar, but also optical sensors. There are several differences between these two kind of sensors. The main difference is related to the frequency that we use to work. In the case of optical sensors, we use light in the class of the infrared, visible, or ultraviolet, while in the microwave, in the radar sensor, we use microwaves. There are several differences. The main is the different frequency and the different wavelength, but also there are also other main differences related to the absorption. So, for instance, the microwave sensor can be used during the night when there are fogs, when the visibility is not perfect, because microwave penetrate objects. So we will see some main difference in the following presentation. I conclude this introduction. The event program is the one that you can see on the screen. A first part on physical sensors, a second part on the advanced applications, and a third part, a roundtable, where we will discuss on remote sensing progress in the United Arab Emirates. I give the floor to the chair of the first session, that is Professor Gianfranco Fornaro of IREA-CNR, to chair the session.
Okay, thank you very much, Vito, for the introduction. So, good morning, ladies and gentlemen. So I am honored to be here to chair the first part of the day. So I'm chairing the session Introduction to Remote Sensing Principles, in which we have two presentations. But before this, I want to just make a comment about the importance of the technology and also of the context that is behind. So we are here to talk about space this week from Italy, and we have heard a lot about the importance of the space for the exploration of the outside, the space for the observation of the planet, and important, first of all, is the observation of the Earth. And Professor Pascazio has given a nice introduction of this topic. What is important, it is called the value chain behind the space. Of course, the space around the Earth is limited. We have a lot of satellites which are used for many applications, like telecommunication, positioning, and of course Earth observation. And what is important is that in the planning of the missions, there must be a value chain. A value chain, that means that there is the part which is related to the development of the mission, the launch of the satellites, the building up of the space infrastructure for the observation of the Earth. And in Italy, we have several times pointed out this concept that we have all the elements of the value chain, but what is important is the last part. The fact that behind this, there must be applications and services. And of course, services are often given and provided by industries, but behind the services, there is research and development of technologies, of methods, and of principles. And so today we are going to give, let's say, the first part of the day is dedicated to the description of the principles. So we have the first presentation that will be given by Professor Pascazio, which is the introduction to the principles of radar remote sensing. So we will discuss about particular sensors which works with the microwaves and operates as radars. Okay, so please, Professor Pascazio, come here again.
Thank you, Gianfranco. Thank you. Okay. On this screen. Thank you. The first slide is my university in Napoli, so I'm very proud to show one of the venue of my university is Napoli. My university is University of Naples Parthenope. Is I don't know if some of us know Napoli. Is a very beautiful city. It is a city where not only Napoli, but Napoli was one of the cities where the first radar study was done in Italy during before and during the Second World War. So we have a long tradition on this topic, and I start from this tradition to show what I'm saying today. Today I will speak about principle of radar system, remote sensing systems, that are one of the two main classes of remote sensing systems, as mentioned before. I did this presentation in cooperation with my colleague, in particular Professor Ferraioli and Professor Schirinzi. So what is radar? Radar is an acronym and means radio detection and ranging. So using radio waves, we can detect objects and we can measure distances. So this was the first purpose of a radar system. The first patent of radars was deposited in early 20th century, so more than one century ago. And nowadays, radars are not only limited to detect objects or to measure their velocity. They can do a lot of things more. We and our colleagues works on advanced application of radar systems, in particular, or of imaging radar systems, to do, for instance, images of the underground. Georadar, ground penetrating radar, very used to understand what is the object or the liquid presence in the underground. So for several purposes, water, oil, or object, or a lot of possible applications. Or watch inside or behind walls, through the wall and intra the wall radar systems are another very advanced application, because you have to model the scattering from this wall. Or, as today we will talk about, obtain high resolution remote sensing images with the new system. The new systems are very powerful, as we will see, as we will present. My colleagues Paolo Gamba and Gianfranco Fornaro will present in the afternoon. So there are a lot of possible ways to use a radar, an antenna that emits electromagnetic waves and register the echoes backscattered by objects. So we can use pulsed. We send the antenna, the transmitting antenna. Very often is the same transmitting antenna that works after as a receiving one, but we can have a bistatic system or a multistatic system, a MIMO system today. So many antennas that transmit and many antennas that receive. So very simply, we are talking about the principle. So we can send a very short pulse. Tau is its duration in time. It can be seen that this duration is related to the inverse of the bandwidth of the signal. So we can talk alternatively or tau or 1 over b. And this is a very important parameter, but on these parameters is related to the spatial resolution of a radar system. The pulse travels from the antenna to the object, to the target. It is reflected and come back, and is registered by the antenna. Or we can use a continuous wave radar. These are used for several applications. We can use also in the stepper frequency way, using pulses of different frequency or same frequency according to the configuration. Also in this case, we send a signal of frequency f or wavelength lambda that is related to the inverse of the frequency, and a signal is backscattered and then received. On the processing of the signal received, processing that we can do, we can detect object, we can measure velocity, we can form images, and so on. One of the basic concepts in radar system, to understand radar system, is the resolution cell. What is the resolution cell? Is a volume in general where if two targets are present simultaneously in the same cell, can be detected as distinct from each other. So if I have 2 or 3 or more targets in the same cell, I cannot detect this target as separate targets. And this cell has a dimension. The dimension is related or to in the range direction, so in the direction from that link the radar with the target is related to the pulse duration or to the inverse of the bandwidth. There is a constant involved that is the speed of the light. And we have 2 angular aperture that depends on the frequency used and on the dimension of the antennas that we use. So, as mentioned before, in the resolution cell, if I have 2 targets present together inside the cell, I cannot detect as distinct, while if the 2 targets are, of course, not in the same cell, I can detect. And I can, in this way, combining different resolution cells, form an image. So the image formation is related to the capacity of detect in the different cell, different targets. In this slide, it is introduced this aperture that is related to the wavelength and to the antenna. And I mentioned before that it can be computed from some parameter of the antenna and of the signal that we use. So, very simply, if we have an aperture, an antenna whose dimension in this direction of the plane is L, and we use a frequency, a working frequency f or alternative a wavelength lambda, we can compute very easily. It depends if the distribution of the current on the aperture is uniform or not, but we can assume that this aperture is related to the ratio between wavelength and dimension. So if we want to understand, not in angle, but in distance, which is the footprint of this antenna, which is the area that is simultaneously illuminated by this antenna, I have to consider that this antenna works at a distance from the target that is named r. So in terms of space, we can compute the resolution of the antenna in this way, so multiplying the aperture for the distance. It's an approximation related to the arc and to the segment at the base of the arc. So a larger antenna, as you see, means a lower resolution, or a smaller lambda, so a higher frequency, means a smaller resolution. So if I use a larger antenna, the beam is narrow and the resolution is better, is smaller. So the spatial resolution, if we consider an image, so a two-dimensional signal, we have two resolution, two dimensions. So we can compute the resolution in range as before as C tau divided by 2, or C divided by 2 and the bandwidth in the range direction. In the cross-range direction, it is related, as mentioned before, by L, lambda over L times R. The factor 1/2 is related to the fact that in case of radar, the antenna works firstly as a transmitting, secondly as a receiving antenna. So the antenna pattern is weighted, multiply each other, so we have a factor 1/2. So the resolution is given by this formula. So as we are speaking today, we will speak about remote sensing systems. This remote sensing system works at hundreds of kilometers from the ground, so the distance is very, very, very large. So I want to understand which kind of antenna dimension I need to obtain such resolutions. So a very simple computation, considering the resolution of the modern system, so more or less 1 meter. We can go, of course, also to lower resolution, but we consider 1 meter. For instance, Cosmos ChemMed is capable to have, with the spotlight mode, images with such resolutions, and we consider a frequency of 10 gigahertz, so a wavelength of 3 centimeters. We consider a distance antenna ground of 800 kilometers. I should need, for 1 meter in range, a bandwidth of 150 megahertz. Okay, it is possible. Several systems have this bandwidth, but we should need an antenna of 12 kilometers. So it is easy to understand that I cannot take an antenna. Even if I'm able to build this antenna, it is really impossible to think that it can fly. And I can take this antenna on an aircraft or a spacecraft. So cannot be realized. So how it is possible to have, as we have, images with such very high resolutions, very small resolution, high, it is better in the language of remote sensing and imaging. So, with imaging radar, and the dimension of the antenna is not physical, but is synthetic. So we can build an array of antenna, not with a real antenna of 12 or 10 or 4 kilometers flying, but with a single smaller antenna that during its orbit occupy different positions in the space, and so synthesize a larger antenna. So in this way, in this world, there is the basic concept of synthetic aperture radar. We can build a synthetic, very big antenna that is able to obtain images with a high resolution, 1 meter or lower than 1 meter. So the modern remote sensing radar system are able to do that. Of course, we work at the microwave, so we use different system with different bandwidth according to the application that we want to do. So if we want to watch forest, we use lower frequency. If we want to have high resolution images of the urban environment, we use higher frequency like X-band and so on. So different systems with 4 different applications. It is important to remember, to underline, that a radar system can work night and day and with any weather condition, thanks to the nature of the radio wave, the microwave to penetrate for instance, fog and other kind of materials. This is a video. Okay, it is not important to watch the video. It is a video that shows that systems like Cosmos ChemEd to exploit this motion use polar orbits because have some positive capability. So in this video, it is shown that the satellite moves around the planet and occupy polar orbit. And during the rotation of the Earth, it is capable to monitor strip of the Earth different because the combined motion of satellite in the polar orbit and of the ground that rotate every 24 hours, it make possible to monitor and to observe all almost all the surface of the Earth. So a tour of the Earth takes less than 2 hours. So the revolution time of a satellite takes less than 2 hours. So in 2 hours, the satellite occupy the same position in the orbit. That does not mean the same position on the Earth, because in the meantime, the Earth is rotated. So this is a simple picture showing the synthetic aperture radar. So this is an aircraft in this way. There is a potential target that we want to monitor. And this target is monitored by different position on the different position during the orbit, during the flight in this case. So a sequence of radar pulses is transmitted and received. And it is important to underline that the formation of a high-resolution image, it is possible because we can do a coherent processing. This sentence is related to one of the sentences of my first part presentation, when I underlined that the wavelength, the frequency and the wavelength between optics and radar system are very different, 5, 6 order different. So in the case of radar, we have a wavelength of the order of centimeters, so 3, 4, 10 centimeters. These make possible to combine coherently, so using the phase, the different pulses. That's why I can focus a high-resolution image. And this is possible, because we use microwaves. Otherwise, it cannot be possible with other kind of radiation like optical. So the same target is visited, is viewed by different positions. So this very simple geometrical image make possible to understand that I can watch the same point, the same target, and so all the point that I want to image with an antenna that is long, the same as the footprint. So because for the similarity of the triangle, it is possible to understand that the range resolution is the resolution that I computed before, so C over 2B. And as the antenna, the synthetic antenna, not the real antenna, the synthetic antenna is larger X, for the reason that I mentioned before, that the resolution, the angular aperture is related inversely to the dimension of the antenna, I can compute the resolution of the synthetic antenna. If you remember the previous formula, there was an L on the denominator, so the real dimension. In this case, we have the synthetic dimension. So this is very large. It is of the order of kilometers. That's why I can obtain this very simple formula that shows that the resolution is half of the dimension, the physical dimension of the antenna, so of the order of meters. From kilometers, this distance is several hundred of kilometers. We can have a resolution of few meters. How to pass from a single target to an image? There are a lot of processing algorithms that were developed from the researchers, but in order to understand it, it's very easy to use this kind of processing that is the first one. So the coupling, the sequence of a range compression and an azimuth compression. So the point target, a single point, so every point on the image has a response that is spread in time and space, so we can do a range compression, then an azimuth compression, so at the end we can obtain the focusing of the single point. So joining on the focusing of all the points of the image, we can reach an high resolution image in SAR. This is for the formation of the image, but it has to remember, as we will see in the presentation of the afternoon, this is the case for not for a point, but for an image. So raw data after compression in range and after compression in azimuth. So the complete two-dimensional focusing. This is the area of Napoli, that is the Vesuvius, that is the volcano of Napoli. This is the city of Napoli, that is the caldera, the other big volcano in Napoli. So it is very known Vesuvius because probably most of us know the Pompeii history, but this volcano is 100 times smaller than this volcano. But this volcano has not a mountain, so and the history of the Vesuvius is very well known for Pompeii. But the very big volcano is that one, the Campi Flegrei, that has a magma underground that is really very, very big, and then it is monitored by a lot of research group, and Gianfranco Fornaro will show very interesting processing of this area, because there is a braid of the volcano, so sometimes moves up and sometimes move down, so it is a macroscopic effect, not millimeters, so several centimeters. So very interesting to see also in the afternoon. These are only a few samples of images obtained with Cosmos SkyMed. Very beautiful. That's why I use this image to show you how an Italian technology can do. Cosmos SkyMed is entirely Italian technology from the industry, research groups, Italian space agency. So it is an entire chain of knowledge between the start and the end of the process. Also, the process was done in Italy, of course. This is a particular of Genoa Airport. Matera, where there is located in south of Italy, where it is located one of the sites of the Italian Space Agency. But just to complete my presentation of principle, when we do coherent processing, we do not stop to simple images. We can do a lot more. And the way is that, as in the stereo vision, if we have 2 points of view with different angle between the 2 points of view, we can recover the third dimension. So in this case, the elevation of the ground. So properly processing the different signal from two slightly different view, it is possible to recover the third dimension. So to recover 3D imaging, but we can do more, 4D image. So we can, the 3 spatial dimension and the time, or new application are 5D image, we can recover other parameters of the scenario that we are monitoring. And this is really the last slide. This is a very modern processing using tomographic reconstruction. So in this case, 3D, I don't show you the 4 and the 5D, and it is possible to locate. This is the loggia, the balcony, the structure that reflect strongly the signal, and it is possible to recover the scatterer positioning exactly in the 3D position on the ground. Thank you for your attention. I hope that I was in the time.
I have the awful task to stick to monitor the time, so we don't want to miss the lunch also. We are a little bit late, but anyway, if there is any question from the audience on the presentation by Vito, if there is anyone. Yes. You have one? Okay.
Should I start? Yeah. So regarding the 3D imaging of the SAR, can it be done using one spacecraft, or should it be like two separate spacecrafts?
No, can be usually is the same. Can be with the same. As mentioned before, the Earth rotates and the satellite rotates in the polar orbit.
Yes.
So after not two following passes, but after a certain number of passes, the satellite monitor the same area. So the same area can be monitored by the same satellite in different time. If these time are not so big, can be done also with the big difference between the two acquisitions in terms of time. But the correlation increases. So the same satellite can be used, or in the case of constellation like Cosmos ChemEd, there is a synergy. So there are few satellites of the same family that can monitor the same area with a smaller revisiting time. Or, as Gianfranco, I don't know if he will show in the afternoon, you can use also different sensors, and you can combine different sensors in some cases. The all important thing that you need two different acquisitions with two slightly different angles, because it's like to have two eyes and to have two different angles watching the same point. So in this way, I can, the brain recover the depth, so recover the third position. Otherwise, with only one eye, you have a flat image and you are not able to recover the third image. Just a quick check.
Just one question.
Yeah.
In your last slide, you have shown us a 3D building model. That was created using ground-based SAR or some
No.
air-based
The satellite.
Satellite-based.
Satellite-based. Satellite at 800 kilometers far orbit.
Then my question is why there is no layover or foreshortening effect in that?
Because you see only one side of the building. The layover is on the other side.
So that is...
Yes, yes.
Okay.
You use, for instance, ascending or descending. So you watch the same side of the building. So what you see is not the layover area, but the scene area of the building.
Okay.
It is geocoded. You estimate the height, and then you can geocode.
Of course, it is geocoded because each scatter is exactly positioned on the real side of the building.
Thank you. Okay, thank you very much, Vito. I think we have to move to the next presentation because really we ran out a lot of the time. So the next presentation will be given by Professor Paolo Gamba from the University of Pavia, and now we are moving to the optical remote sensing. Please have a nice presentation.
Thank you, Gianfranco. Yeah, thank you. Okay. Number 2. I'm sorry. So my task is a little bit easier because I'm going to talk about optical remote sensing that is closer to what we know and we see. So it's hopefully, but just a few words about the University of Pavia. The University of Pavia is a university in the north of Italy. It's very small, but it's one of the oldest in Europe. It's 650 years old. So we started quite some time ago. Of course, not speaking about satellite and sensors, but that's okay. So I'm talking about optical remote sensing. And as Vito was mentioning, the passive optical sensor relies on external emission of electromagnetic waves, typically from the sun, but not only, because we know that the target itself, so the Earth, is also emitting some sort of energy. They have a lower complexity with respect to SAR. That's why I'm saying lower. And less energy consumption, because they are not active, they are passive. They just wait for something to arrive. We have different examples, and I'm going to talk about multispectral, hyperspectral, because the Italian experience is now starting to be on top of the other activities with respect to hyperspectral sensor and nighttime light sensor, because I'm working on urban areas, and which is very important. So this is typically what happens when you think about a photo camera. It's a CCD array, so coupled charge array, which is typically getting images in the visible. So you see the visible from 400 nanometer to 900 nanometer, and the near infrared. The typical application is for photogrammetry and mapping. When you talk about satellite, you need to change a little bit the idea, because since you are far, basically the energy that arrives is lower. That's typical when you see a lamp here, it's very bright. If you see the same lamp from very far away, it becomes much less bright. So this is a point-wise collection of radiance, but it's done at different wavelength. So not only red, green, and blue, which is usually what we think about visible, but also near infrared, and sometimes other different type of infrared. So multispectral sensors have a few bands, and around a bandwidth, so you know the frequencies that we are collecting are basically around 100 nanometers, and we have 3 bands, red, green, and blue, in the visible range usually. When you consider what is the newest application, they correspond to the so-called imaging spectrometers, which are similar to multispectral sensors, but they have many more bands. So they just sample the same energy, but with different, much better, which means that it's finer, narrow bandwidth, so you just look for smaller things, and of course you get less energy. Because if you get something which is, you subdivide the whole energy in many different slices instead of a few slices. So the energy is smaller. So it means that if you want to get something that your sensor is able to collect, and it's not only noise, you need to collect more energy. That's why you need to collect something on a bigger area. So the resolution of the imaging spectrometer from satellite is actually lower. That's the disadvantage. Now, the Italian Space Agency has recently launched the Prisma, which has an Italian name, so Precursore Iperspettrale della Missione Applicativa, which is an optical payload with an hyperspectral imager that I'm going to show some result on this area in the afternoon. And so how they work? Okay, every satellite, as you know, is actually rotating around the Earth. What happens is that in order to collect information from the satellite, the previous satellite, I mean the first Landsat system, they basically used whisk broom scanner, which is basically like a whisk broom. So they basically get information by scanning line by line while the satellite is moving. So you see here, you just scan and go around. The next generation is actually moving to the push broom scanning, which is basically acquiring every single line, and then because the satellite is moving, you get one line, another line, another line, another line, and eventually you have an image. So that's the idea. Instead of having one point by point, you have basically one line by line. And actually, it's easier. Then how you get different wavelength? You get different wavelength by considering the fact that you have the image, and which is entering, and then you use what is called a dispersing element, which is a prism, which is basically subdividing the different colors of the image, the different wavelengths, in your spectral, and spatial image. Okay, so you have both the space, every line, every single pixel there, and then you have all the information on the spectral line. So this is called multispectral scanning, okay? Now, if you have only a few bands, you don't need a prism which is able to subdivide every possible wavelength. You use a different system which is called a dichroic mirror. So a mirror which is actually taking only one color and letting every other color pass. So you see here, you have all the image which is arriving, so all the, let's say, all the light here, then is focused, and here you have the first one, which is basically collecting only the blue color, then the red color, then the other infrared color. So you have one mirror, which is made by a particular material that basically reflect only one color and let every other color pass. Then you take one color at a time. It's easier if you have a few, but if you have more, you cannot have 100 of different mirrors here. That becomes much, much, much more complex. Okay, so what actually we get when we have an optical multispectral sensor? What we have is what we call a, let's say, a sampled version of the reflectance by a particular material. So let's consider for the moment that we have a tree, okay? If we have a tree, we know that the sun illuminates a tree, and then what happens is that part of the light coming from the sun is absorbed by the tree, and some of it is instead reflected. The one which is absorbed by the different chlorophyll, chlorophyll A and chlorophyll B. In vegetation, we have two types of chlorophylls. And then the part which is reflected is the green, and this is the reason why we see that, you know, everything here is green. I mean, the vegetation is green, and the infrared. Now, we don't see every wavelength because we have a sampling, so we just take some of the bandwidth. Therefore, what happens more precisely is that we have this quantity, this idea. So we have a number of points that correspond to what is collected at different wavelengths by the sensor. And we have a sampled version of the overall thing. And using that, we can obtain different indexes or different images, which are useful in order to understand. So, for instance, if we take the blue, the green, and the yellow, the blue, the green, and the red, we just, and we collect information, we get what we call a true color image. So an image of the surface of the Earth, which is very similar to what we see with our eyes. And you see the vegetation here is in red. But in many, many multiple cases, if you're talking about vegetation, what we usually consider is the fact that we use the fact that the vegetation is very reflective in the near infrared. And so we use this type of image, which is called a false color image, because these colors are not natural. And this is much better for vegetation. Why? Because the green, you see here, sorry, this is the real red. The green, which was this one, and this one is the near infrared. Now, if you color the image according to this quantity, this one is much bigger, so it's much brighter. So you see much more the information about the vegetation, and it is possible, because this is very large range, to understand also which are the difference between the different vegetation. So vegetation which is very healthy, with a lot of green, and vegetation which is instead very poor, because you don't have water enough, and therefore it goes to the brown version, okay? So by using this type of images, we are able, we have more than red, green, and blue, and we use this type of, okay, here I'm using a multispectral data coming from the Sentinel-2. Sentinel-2 is the multispectral sensor by the European Space Agency. It's actually not one sensor, there are two or Sentinel-2 A and B, and now the ESA, the European Space Agency, is working to the multispectral next generation, Sentinel next generation, which is very interesting. Okay, just to give you a few application examples, and then I'm closing, I hope in time. Of course, this can be used for precision farming. Those are examples which are historical examples. Most of you may know them. They are based on Landsat data. This is precision farming. This is a computation of an index that gives you information about where water is missing in a specific field. So we get also the information where we need to put water if you don't have much. Another information is about biomass. Here, just using multiple bands, you can see where the trees were cut. And this is a typical application, for instance, in the Amazon forest. There's a lot of issues there. Vegetation monitoring as well. This is mostly related to the quality of the vegetation, type of vegetation. Another important application, which is at the moment also interesting because you know that there is a big volcanic eruption right now in the La Palma, which one of the Canary Islands. And it is possible to obtain information about the plumes, so what type of, where is it going, what type of gas, and also the ashes, which are also very important in order to understand what type of things had happened. We have also another application which is also important, is the watercolor. The watercolor is basically an application related to the quality of the water. In Italy, this is typically something that we are very concerned because we have, as you know, a number of lakes in the, and also the Mediterranean Sea, which is around Italy, is not very large. Therefore, what we have is basically that the water there is staying, and so we need to understand well what is the type of sediment which are in the water. And this is something that you can go by just looking, but of course using satellite and optical satellite you get much better information. And again, wildfire, which is typically another application in Europe and in Italy as well. I'm just going to conclude by giving you, as a last slide, a special case of an optical satellite, optical sensor, which is at the moment used in order to monitor human activities. So directly where most of the people are, and indirectly where most of the buildings are, because we know that humans usually are inside or close to building. These are the nighttime lights, which are light which are observed from the surface of the Earth at night. So artificial lights, and those provide information about where are the people staying and a lot about also the activity which are connected to this. And just to give you an idea that there are also unconventional way to use multispectral data in order to obtain information which is beyond what people were considering, because this data come from a meteorological system which was actually there in order to get information about the weather. Okay, that's it for today. Then in the afternoon I will show you some example using Prisma data for that. Thank you very much.
Thank you very much, Paolo. Thank you very much, Paolo, for also for gaining a little bit of time for the presentation. If there is any question from the audience. Okay. If this is not the case, then we can move on the next part of the morning activities, which now enters the parts of demonstration. So we just need a little bit of time for moving the computers here. So now we are running the interactive demonstration. We have two parts. The first one will be dedicated to the demonstration of the basic principles behind the radar, what we have talked in the first presentation. This part will be handled by Michele Ambrosiano and Stefano Franceschini. Okay, and then we will have also demonstration part also with examples given in a GIS environment by the other part of the team, in particular by Giampaolo Ferraioli, Sergio Vitale, and Maddalena Autorino. So please start with your presentation. I think that you need also the.
Well, firstly, I don't know if the microphone
okay.
is working. Can you hear me?
That's perfect.
Oh, it's on the other side. Okay, yeah. This first part of the presentation is just slides, and then we will move on with the live demonstration. So thank you very much, Professor Fornaro, for the introduction, and I'd like to thank the audience for joining also this live demonstration. So today we are going to show you a very simple demonstration regarding the basics of radar introduced in the previous talks. Okay, so let's move on. The whole demonstration is divided, this presentation, in 3 main experiments. Okay, the first one is related to distance estimation, as we will see. There's a second part more focused on the concept of resolution, okay, related to radar applications. And then a third part regarding velocity estimation, as you can see. So we will see firstly the case of a static target, and then we will move on with the moving object, okay? And we will try to estimate its velocity. Okay, I will not go deep in detail because the previous talks have already talked a lot about radar. Simply here, I want to remind you what a radar does. It's a system that exploits electromagnetic waves in the microwave frequency bandwidth in order to detect and determine a target position, okay? Both if it is static or dynamic, okay? It's moving or not. What is important here, and I want to underline, is that this is possible thanks to timing. What I mean is that it's important to measure the time, okay, since the start of the signal, and to measure the distance with the time you receive the echo. So, thanks to this information, we are able to retrieve the target position. Well, regarding spatial resolution, this is a very general concept also for plenty of systems, okay? What do we mean with spatial resolution? Is the capability of the system to identify 2 different objects as separated, okay? So the minimum radial distance between targets at which they can be imaged as separated. In an ideal case, that is the one that you see in this slide, it's quite easy. I mean, this is the best option, the ideal case, in which we have 2 targets at 2 different distances. And after transmitting a signal, we're able to collect the echo coming from these targets. And even if this echo would be very close, you would be able to identify the 2 targets because they are like impulse, okay? Very narrow, very strict. So, but this is the ideal case. In practice, we don't have this. In practice, we have something like this. These are not exactly the echoes, but is an information related to the echoes after a proper processing, okay? So we don't have spikes, but we have something that is spread, okay? So if you think these 2, let me say echoes, if they are close, because the targets are close, they will merge each other, okay? So you will be not able to image the 2 targets as separate anymore, okay? So this is a general concept, not only for radars. So what kind of pulse we use practically in radar? We use a chirp pulse, okay? Every radar uses this kind of pulse. Why? This is a convenient kind of signal because it allows to keep a low power peak, okay, even with a long, duration signal, but with a large bandwidth, but allowing us to get the same results of a narrow, very narrow signal with a high peak power. Okay, so what is a chirp? Is what you see on the left-hand side of this slide. Okay, it's a signal that is oscillating, and is a linearly frequency modulated signal. That means that the more the time passes, the higher the frequency. In this case, the higher the frequency is. And so you can see because the number of oscillation increases per unit of time. So this is the case. And thanks to this kind of signal, we are able to improve the resolution and to get this situation. Okay. Of course, it's important. The capability to resolve the object is related to this parameter that is the bandwidth of the signal. Okay. So Okay, let's go to the practical part. This is just it's a sketch of the demonstration, or better, of the hardware, or the toys for engineers that we are going to talk about, okay? You can see we will use a signal generator, that is this one, sketched here in this slide, that generates the chirp signal for our live demo. This signal is also shown on the oscilloscope here, and also collected by this device here that you can see, that is a analog to digital converter, okay? So to collect the signal. And of course, the signal has to be transmitted thanks to a proper sensor that works like an antenna, okay? Later we will see better in detail this thing. So the signal is transmitted, hits, impinges on the target, and the backscatter signal, or the scatter signal, is collected by receiver, sampled by the analog to digital converter, and sent to the laptop for proper processing, okay, to locate the target. Okay, so one important thing is here, all these instruments don't look like radar, but this is an acoustic radar, okay? Why we brought this is simply because it's easier to carry, okay, and it's cheaper. So for this demonstration, we decided to show this, but the principles are the same, even though the physics is slightly different, okay? So let's go to our first experiments we are going to show you. That is the estimation of the distance of the targets, and of course we will see also the resolution, okay? If we will be able to retrieve the two objects or not according to the nominal resolution. Okay, so firstly we will start with the calibration. Okay, here, sorry, have a look here on this video. So let's start with the calibration step. And so maybe it's not the best option to look at the device, but anyway, what we are doing here is sending a chirp. This is for the calibration, then the calibration is completed. We will try with the first case, as you can see here. Okay, now we have a certain target. Later we will measure the distance, and we want to see, with the distance estimation, we want to see if the target is properly located. I mean, if we are able to estimate the distance from the system. Okay, as you can see, the target is approximately at 20 centimeters far from the device. Of course, even by having a look, it's possible to check, but it's 20 centimeters. Sorry? Modern device. This is the highest technology I have. Sorry. Anyway, for those of whom that want to check, maybe later we can have a look, a better look. Okay, so for a single target, we were able to locate the target. Let's move on. Let's try with the case of two targets, okay? Just a moment. This is a very professional device, in-house, a very in-house system. Sorry for the, but
How much it costs?
that's very nice, because the whole system might cost less than 100 euros, but much less, okay? If you include also, apart from the device, of course, for the instrument. If you want, you can come closer, of course. Maybe it's easier also to look here. Also, because it's nice, you can have also a look at to see also the chirp generated here. If you have a look at the oscilloscope, just a moment. If you have a look at the oscilloscope, you can see the chirp. I mean, the oscillation changing in frequency. Okay. Okay, and here you can see the frequency we are using for the chirp. To simply for your information, is a chirp from 38 kilohertz to 37.5 to 42.5 kilohertz. So please, let's see this other case. Let's see, oh sorry, here is the... Fingers crossed, it worked. So here you can see, of course there is still the previous target, and that's okay, of course. And there's another one, approximately more than 30 centimeters. If you trust me, but you can see the distance is, this is very important. In this case, we were able to resolve the two targets because I haven't told you this, because the targets are separated, are at a distance each other that is above the nominal resolution. Okay, so we are able to identify the two targets. Sorry? Nominal resolution in this case with this bandwidth and for these ultrasonic sensors is 5 centimeter. Here we are 10 centimeter approximately. Regarding the antennas, if you want to have a look, this is a cheap device. I mean, these are just our antennas, our acoustic antennas. It's very cheap. Try to guess how much is it for one of these. I'm not going to sell them, of course, and so but I can say that it's very, very cheap. Try to guess if you want. More or less, you are not that much far. It's 2.5 euros, so let's say 10 AAD approximately should be. So it's cheap. Now you can understand why this is more convenient to carry and for the demonstration. Okay, but of course radar is the same. So now let's move on. Let's see the third example, last example of the other situation, in which the targets are below resolution. Okay, so they are close. They should be at a distance lower than. Sorry, this is very nice. It looks like an abacus to me. Don't know if you remember this kind of. Yeah. So now they are at a distance that is below the 5 centimeter. They are still moving. Sorry for the. Okay, let's try now. So now the two targets are at a distance below the resolution. What we do expect? We expect that these 2 points merge in one single target, because as Professor Pascazio said in his talk, they are in the same resolution cell. Let me say like that. Okay, this is just 1D plot, but let's see what happens in this case. So you see. Okay, because the other target now is farther than the previous case, so the point is a little more over the 30 centimeter. Okay. Later, if you want to have a look, closer to the device, we can check also the distance if you want. Okay. Well, for this first part of demonstration, it's okay. Now let's go back to the presentation for the last part. That is the last example, please. Thank you. Is it possible to go back to the presentation, please? Ah, yeah, sorry. Right, I forgot to. Okay, so let's move on. One last piece of information about theoretical stuff. Well, we consider the case of static targets, and we consider the case of a pulse, okay, a cheap pulse. Now we are moving on, and we want to retrieve information about the velocity of the target. And in this case, we are exploiting a continuous wave radar, okay? So it's not an impulse anymore. And to do that, we exploit a very well-known effect that you experience every day in your life. That is the Doppler effect. It's the one that you perceive when the siren is moving, for instance, an ambulance or a police car is moving towards or far from you, okay? You hear, but pay attention, you hear a different sound, okay? The more it gets closer or farther from you. But pay attention, in fact, not to the intensity of the signal, to the frequency, okay, that you receive. So the Doppler effect is an apparent change in the frequency, that is also named the shift Doppler, that is related to a relative movement between the source of the signal and the receiver, okay? In this case, if you see the animation there is a source that is emitting at a certain frequency, okay? So it's continuous wave, single frequency emission, but the target is moving towards the observer. So the closer you see that number of these waves, number of oscillations is increasing when moving towards the target, and towards the receiver, the observer, and becomes less when you go farther from the observer. So this is the shift Doppler. So if we are able to measure this quantity, we can retrieve information about the velocity of the target, right? Because we know the velocity, the speed of propagation inside the medium, the f0 frequency. So and this quantity is measured, so we can get the velocity estimation, right? Last part, last example, we will see a moving target, still with a very technological system, okay? That is just human movement, okay? I just pushed this. Yes, grazie Stefano. Okay, now we have just a single target. I'll show you what happens when the target moves. Okay, we want to retrieve to estimate its velocity. What is important to say is that we are able to estimate the component of the velocity along the line of sight of the system, okay? So this is important. So I'll try now to move the target like a pendulum. Look, hopefully I hope not to destroy the system with that. And here you can see this representation that is a velocity time representation that is also a frequency time representation. When you can see this oscillation, not very clear, I should move more the target. Now we'll do another try. Because when the movement is bigger, the oscillations are longer, you can see this kind of movements. Let's make another try simply to show you. Yeah, grazie Stefano. It was too much soft in pushing the... Okay, more or less now it's more clear, okay? You can see just the velocity, the velocity is changing. When you see, maybe here is not that much clear, but you can see that there is also a damping related to the okay, perfect, even perfect like this. Okay, yeah, so the damping effect is more limited. And now you start to see. Now you see the code. If you are interested in the code, we can also discuss the code, but I think it's better to see the results for now. Now it's nice, isn't it? So you see, okay. So we decide to, if you wait a little more, you start to see the damping effect of the pendulum, okay? So now it's much clearer. More, it depends on the movement. I told you it's on the line of sight, so it's better. The more you are on the line of sight, the better is this image. Look, okay? Of course, this is and now you have also an idea of the damping effects, okay? What is this representation? If you see here, of course, you have to have a look to the yellow line, okay, the yellow part that are related to the movement. So you see, negative values correspond to movement far from the setup, and the positive peak is towards, so higher frequency and higher velocity. Last thing that I want to show you, and then we complete our talk, is another case. I told you that this is the results along the line of sight. But so what happens if I do this? Okay, what do I expect from this? Do you have no change? In the ideal case, yes, because I'm a human, I will not be that much able to give the right direction. But of course, what we can say, have a look to what now is the value, approximately -1 + 1, okay? Now what I expect is a reduction of these peaks, okay? Let's try to have a look. Okay, yeah. Sorry, it's my... But you can see anyway that the amplitude of this oscillation is reduced, okay? So it depends also on the moment. Well, so thank you very much for your attention. If you have any question...
Thank you very much, Michele, for this
thank you.
Very nice presentation
of
the concept, and also for the pocket radar that we have now developed. I don't know if there is any question.
I do have one regarding the velocity.
Yes.
Are you doing any frequency, like I mean, Fourier
Exactly. You are right. For time constraints, I haven't gone into deeper detail. If you see this representation, this is named spectrogram. Basically, it's a short time Fourier transform. It's like you select a window, a moving window, and you do the Fourier transform, a short time Fourier transform in that window. So you get information about the frequency and time. Of course, you need a trade-off between these two, between the sides of the window, okay? And of course, the resolution that you want to get, because these two things are related. So, thank you anyway.
Okay, Michele, I have to stop you because we need to
move on.
go.
Okay.
Thank you also for the explanation of the fact that we see the velocity component along the radar line of sight, which is a concept that we will also see this afternoon by the satellites, more or less the same. Okay, next is the presentation on the multi-hyperspectral part that will be given by Giampaolo Ferraioli, Sergio Vitale, and Maddalena Autorino.
Thank you very much. So in this second part, we will focus on multispectral system. So we'll have a little, very short demonstration about what we can do with the multispectral system. And I go just further recall what Paolo Gamba said before. So we are using multispectral, so we are meaning passive optical and multispectral system. We mean that we need an external source of illumination or radiation, and usually we use solar radiation. And when we talk about multispectral, we mean that we have information from different spectral bands. So what we usually have is we work with this kind, we see usually this kind of images. So our brain works, let's say, in RGB, so our eyes combine these different bands. So what we usually have is a scene like this. We see this kind of field. But if we change the lens that we're using for observing, we can have multispectral images. So for example, we can see this land in different ways. So this is very nice because, as a matter of fact, if we have different bands, we can see different things. We can see hidden things, so things that our eyes cannot see. And so we can extract information, extract features that are hidden, or enhance features. For example, by combining different bands. And one of the most used index is this one. It's called NDVI, which is used for vegetation, and it's very useful because it enhances some aspects. So what are we going to show you? It's something based on a very simple camera. Here is a picture, but we have the camera here, and it's a very low-cost camera. The cost is about approximately 4,000 dinar. And what happened in this camera is mainly, if you see, is like an action camera, common action camera. And the different thing from an action camera is that this filter, this lens, is not RGB, but is this one, OCN, which is orange, cyan, I don't know exactly in English, and near infrared. And what does this mean? That mainly it has these three filters. And so we are going to use this camera to show what we can see, what our eyes cannot see, but what actually we can see with this camera. So we show just some example of this. And these are the characteristics, very good, for example, ground sample distance, the weight, and especially, I mean, the cost of the thing. Sergio, so please, if you want to start a little demonstration with this. We're going to show a picture in here. Just probably the light is not the perfect one because we are not using, we don't have the exact sun radiation, but I can,
yes. Good morning to everyone. As Professor Ferraioli said before, I show you the effect of this camera. As you see, these are two normal plants that are more similar as color when you see it from there. Now I take a picture from this camera. Okay, and I show you how to compute, how to see the enhancement, how to enhance this effect. Now I collect this camera, take you images in raw data, so you can process them from scratch. Okay, just a moment. You can process from the raw data in order to get the information that you need with a software. In this case, we used the software of this camera, but there are much others. And with another software, after that process is complete, you can acquire the information that the professor was explaining before. In this case, you can extract the information, for example, the NDY index that was described before, just combining the bands. So we got the third band, that in this case is the near. In this other case, we subtract the cyan. And we made a normalization of this index. And just we save the image. And that's it. As you see, this cactus is much more bright than the other vegetation. This because this cactus is true. This plant is a fake plant. So now we cannot go further in this demonstration, so we have some slides that are already ready, and I leave the floor to my colleague, Maddalena Torino. Ah, okay, yes.
Allora, questo no, ok, grazie.
Okay. Is the sensor near infrared included?
Yes, there is
Okay.
near infrared also.
3 bands, yeah, and one of them is near infrared.
But is it modified? Because I know that this GoPro, right?
No.
Ah, okay. Because it's the same shape.
No brand. Exactly. The thing is the shape of a GoPro.
Yeah.
These are exactly the same shape and same structure as a action camera like a GoPro.
Alright.
The microphone. Okay. So it has exactly the same shape, common, very known action camera, but the length, the filter is different. So actually, what they made, this company, the company that made this kind of camera, just used the same structure, but they changed the length, the filter. So it has, you can find the different filters. In this case, it's OCN, but there are several others.
Just to point it out.
Yeah. When I was telling, no.
Please, Maddalena.
Okay, thank you. I will show some easy and clear examples of what is possible to see with this kind of camera, multispectral camera, and what is possible to see with the multispectral camera, and that is not possible to see with a standard camera, for example, the smartphone camera. For example, this is the first example. We took some pictures a few days ago in Dubai. This example shows a true plant. What is expected is that in a multispectral camera, we see a high value where we find the true plant. But what we can see see is that there is a black area in the image. This is because we put inside the plant, the true plant, this fake plant. What I want to show is that with a normal picture obtained by a normal camera, we don't see the fake one, the fake plant, but with the NDVI index, we can see the fake plant. Another example is this palm tree. In this case, we want to underline that with the NDVI index, we can distinguish healthy leaves from non-healthy leaves, because typically the new leaves of the plant are in the upper area, and in the bottom we have the old leaves. So in the NDVI index, the value are high for the new leaves, but are lower for the old leaves in the bottom. This is the same for two leaves. One is a healthy leaf, and the second on the bottom is an unhealthy leaf. So the NDVI index is high for the healthy leaf. This is a nice example because here what is expected is that all the vegetation, all the plants appear high in NDVI, this is what happened. But also the reflection of the plant are enhanced with the multispectral camera and the NDVI index, as we can see in the swimming pool or in the bay, in the canal on the back. Okay, this is the last example I want to show. On the left, we have a arm. And we can see the superficial blood vessels, but we can enhance these superficial blood vessels with the same technique, the multispectral camera and the NDVI index, because of due to the different absorption of the vessel and the skin, different absorption and different reflection. Thank you. Thank you very much.
Thank you, Maddalena. See, is it working? Thank you, Maddalena, and thank you also to Stefano for the blood.
Yes.
I think that this ends the presentation of the morning. Now we have the lunch break, and we will come back in the afternoon for the applicative session. Thank you very much, and I would like to give an applause to all the speakers of the session.
Thank you.